So all the data are collected with Bruker dimension icon IR. So I'll start with a sort of standard or model system that's PS-LDPE. PS is polystyrene and low density polyethylene. So we have these two polymers blend together. So as usual, if we take an AFM image at the left, so you see the round circular domains there and the matrix. Now for IR, so one of the mode is we can just go to one location, one XY location of the sample, for example here, and we can take a spectra. So that's a point spectroscopy. And if we go to the circular, the round domain, and we can take a spectral there. So this is one mode, point spectroscopy. Now, if you are an experienced spectroscopist, right, because the spectra you got is really, I wouldn't say matching the FTIR, but it's very, very close. So you can either tell from your experience or compare with a database spectrum. You can see, oh, okay, you see that 3 on the green spectrum. You see the 3 peaks there, you know right away that's polystyrene. And similarly, if you look at that 2 peaks, you know it's polyethylene. So basically, it tells you the round spot polyethylene and the matrix polystyrene. So that's one mode. And now if the other mode is, now if we pick a wheel number, for example, the 1490-93-ish, and let's see, we can take a map. So let's look at this one. And if we take a map at 1490 centimeter inverse at that wheel number, and if you take an image, and you can see the matrix is lighting up, right? So it tells you that's the polystyrene part. And then if you take another map at a 1464 centimeter inverse, you see the round domains lights up. So that's the IR mapping mode we have here. It's quite straightforward. So now if we put all those mechanical properties, electrical properties together, let's see what we have here. So again, here on the right side, I'm showing the chemical map we just took. And then let's say on the mechanical side, you can see the adhesion map with peak force Q and M. You see the adhesion map there. And clearly, on the polyethylene part, it's stickier than the polystyrene part, the matrix. And if you look at the elastic modulus, and polyethylene, the round part has lower modulus versus the matrix polystyrene has a much higher modulus. For the KPFM, if we do a electrical measurement on the sample on the same location, what do we see here at the top, the potential map, that's really the work function difference, work function contrast map. And you can see over the polyethylene, it has a little higher work function, and polystyrene slightly lower. So I want to point out what we are seeing here, not actually the work function of the polymer itself. It's actually the underlying substrate. It's a silicon, and the polymer, the dipoles of the polymer actually alters or modifies the work function of the silicon a little bit to make it either higher or lower. So it tells a story or some information of the bottom layer of the polymer. In the meantime, you can also get the dielectric contrast map, dielectric constant map down there. It's qualitative, but you can see it there as well. So with all the different techniques, now we have chemical, we have electrical, we have mechanical, each telling some story about the sample, and together we can have a better understanding of the sample. So now move on to a more real world sample, SBR. It's a synthetic rubber. It has polystyrene and butadiene there. That's why SBR there. So this sample or polymer or rubber actually is used for car tires and accounts about probably close to 50% of the car tires. Now let's take a AFM image and also use peak force QM. We can see the modulus, the allocation there. So why do we care? As a car tire, what we care is mechanical wear resistance, and also we care about the friction, right? When the tire hits the road, right? Meets the rubber meets the road, and we do care about the friction as well. So this is the mechanical part. You may wonder, what are those particles? This sample actually is the SBR rubber, and it has some carbon black filler. The reason to have those carbon black filler is to enhance the mechanical resistance. You can see on the modulus map, over those particles, the modulus is much higher. That will increase the lifetime of the tire. So now let's do a chemical map, IR map, right? We want to know where butadiene is, and we choose a wave number corresponding to butadiene, and we see a map there. And then if we want to see styrene, where the S is, and we choose a wave number for that, it's a 1601, we get a map. And now we have a question actually. See if these two maps look so similar, right? Even if we take an IR map, add a wave number, where there's not much absorption, no IR peak, we still see something similar. This was initially puzzling a little bit. So what's going on here? We can't tell right away which is which. So end up what's happening here is, since we have carbon black there, and carbon black absorb IR almost across the whole wavelength range. So no matter where you go, you always the carbon black absorption always dominates. So how to solve this problem? So what we do is we can actually do a ratio map. That is to, let's say, for example, if we divide the butadiene map by the 1180, that map, and we get a picture below. Now we can see actually over the carbon black and little signal there, and away from there, you see stronger signal for butadiene. Similarly, but on the opposite, over those carbon blacks, we see stronger styrene signals. Now, if we do a ratio map of the butadiene versus the styrene, actually we get the picture down here. Now you can see again over the carbon black particles, and you have a weaker signal there, so the ratio of butadiene is lower, and away from there, the ratio of the styrene ratio is higher, signal is higher. So we can see something. Yeah, we speculate, there may be some phase separation. So here we go. We can see it clearly.